Our universe is vast. It's filled with billions upon billions of stars. Each star is a sun, often with its own planets. Imagine that. Planets of all sizes, compositions and possibilities. The sheer scale of the cosmos is almost impossible to grasp. Yet, amidst this immensity, we find ourselves in a tiny corner, orbiting a rather ordinary star. Welcome to our solar system, a place of both familiarity and profound mystery. Our solar system is more than just a collection of planets orbiting a star. It's a complex system shaped by gravity, time and chance. It's a place of incredible diversity, with each planet boasting its own unique characteristics and history. Take Mercury, for example. It's a small, rocky world, whipped by solar winds and baked by the sun's intense heat. Venus, shrouded in thick clouds of sulfuric acid, experiences a runaway greenhouse effect, making it the hottest planet in our solar system. Then there's Earth, our home, a blue and green oasis teeming with life. Our planet's unique combination of liquid water, a protective atmosphere and a stable climate has allowed life to flourish for billions of years. For centuries, humans have gazed up at the night sky, mesmerized by the celestial dance of the planets. The solar system, with its promise of alien landscapes and untold wonders, has always captivated our imaginations. Today, that fascination continues to drive us to explore the cosmos, seeking answers to fundamental questions about our place in the universe. We send robotic explorers to distant worlds, venturing further and further into the unknown. These missions, driven by human curiosity and ingenuity, have revolutionized our understanding of the solar system. They've revealed the intricate details of planetary surfaces, the complex dynamics of planetary atmospheres, and the hidden oceans that may exist beneath the icy shells of distant moons. The exploration of our solar system is not merely an academic pursuit, it's a testament to the human spirit of discovery, a desire to push the boundaries of knowledge and explore the unknown. By studying other planets, we gain a deeper understanding of our own. We learn about the forces that shaped our planet, the delicate balance that sustains life, and the challenges we face in preserving our home for future generations. Moreover, the search for life beyond Earth, whether microbial or more complex, is one of the most profound scientific endeavors of our time. The discovery of even the simplest life form on another planet would have profound implications, fundamentally altering our understanding of life in the universe. It would tell us that we are not alone, that life is not a cosmic fluke, but rather a possibility woven into the very fabric of the cosmos. Our journey through the solar system is about to begin. Fasten your seatbelts and prepare to be amazed as we venture into the heart of our cosmic neighborhood. We'll encounter scorching heat, bone-chilling cold, and wonders that defy imagination. We'll explore planets that resemble our own and others that seem like they belong in science fiction. Get ready to be humbled by the sheer scale and grandeur of our solar system. Prepare to be surprised by the unexpected beauty and diversity we find along the way. Most importantly, get ready to have your perspective shifted as we delve into the mysteries of our cosmic backyard and contemplate our place in the grand tapestry of the universe. Our first stop, the sun, the star that makes life on Earth possible. We'll journey to its fiery heart, where nuclear fusion unleashes unimaginable energy, and then we'll trace the path of sunlight as it travels across the solar system, illuminating the planets and moons that call it home. So buckle up, space travelers. Our adventure is just beginning. Our journey through the solar system begins with a visit to the innermost planet, Mercury, a celestial sentinel that tirelessly circles the sun. Imagine a world where the sun dominates the sky, a fiery orb appearing 3 times larger than it does from Earth. This is the reality for Mercury, a planet locked in a gravitational dance with our star, its surface bearing the scars of this fiery relationship. Mercury's proximity to the sun makes it a world of extremes. Temperatures on its surface can soar to a staggering 800 degrees Fahrenheit or 430 degrees Celsius during the day, hot enough to melt lead. But as night falls, and with no substantial atmosphere to trap the heat, the temperature plummets to minus 290 degrees Fahrenheit or minus 180 degrees Celsius. This extreme temperature swing is the most dramatic in our entire solar system, a testament to the power of our sun and the unforgiving nature of space. Despite its harsh conditions, Mercury is a captivating world, full of intrigue and scientific value. Its heavily cratered surface, reminiscent of our own moon, tells a tale of ancient impacts, a testament to the violent early days of our solar system. These craters, some of which are hundreds of kilometers across, are preserved in pristine condition thanks to Mercury's almost non-existent atmosphere. One of the most intriguing features of Mercury is its surprisingly large iron core, which makes up a significant portion of the planet's interior. Scientists believe that this oversized core might be the result of a massive impact early in Mercury's history, perhaps stripping away much of its outer layers and leaving behind a dense, metal-rich world. This theory, though still debated, highlights the dramatic events that shaped our solar system's early evolution. Imagine standing on the surface of Mercury. If you could withstand the searing heat, the sun would dominate the sky, an unblinking eye casting long, harsh shadows across the desolate landscape. The sky itself would be black, even in daytime, due to the lack of an atmosphere to scatter sunlight. The stars would be ever present, piercing points of light against the inky blackness. The surface of Mercury is a testament to the power of impacts. Craters of all sizes pockmark the landscape, some ringed by towering cliffs and others filled with smooth plains of solidified lava. These impact basins tell a story of a tumultuous past, a time when the early solar system was a chaotic shooting gallery of asteroids and comets. Despite its seemingly barren appearance, Mercury's surface is far from static. The planet experiences a phenomenon known as Mercury quakes, tremors that ripple through its crust. These quakes are thought to be caused by the planet's interior cooling and contracting, a process that has been ongoing for billions of years. These subtle movements remind us that even seemingly dead worlds can still be geologically active. One of the most remarkable features on Mercury is the Caloris Basin, a colossal impact crater spanning 1,550 kilometers or 960 miles in diameter. This immense scar, formed by an impact early in the solar system's history, is one of the largest impact basins in our cosmic neighborhood. The impact that created Caloris was so powerful that it sent shockwaves rippling through the planet, creating a region of chaotic terrain on the opposite side of Mercury. Leaving the scorched plains of Mercury behind, we venture further out from the Sun to encounter Venus, our nearest planetary neighbor. Shrouded in a perpetual veil of thick, swirling clouds, Venus has long held a certain mystique, captivating astronomers for centuries with its enigmatic beauty and tantalizing secrets. From Earth, Venus appears as a brilliant point of light in the night sky, often outshining every other star. This dazzling appearance is due to its highly reflective cloud cover, which reflects about 70% of the sunlight that falls upon it. These clouds, however, are not the gentle, fluffy formations we associate with Earth. Instead, they are composed primarily of sulfuric acid, a highly corrosive substance that would be deadly to humans. Beneath this toxic shroud lies a landscape sculpted by intense heat and volcanic activity. Venus boasts a runaway greenhouse effect, where heat from the sun is trapped by its dense atmosphere, leading to surface temperatures that can reach a staggering 900 degrees Fahrenheit or 475 degrees Celsius, hot enough to melt lead. This extreme heat makes Venus the hottest planet in our solar system, even hotter than Mercury, despite being farther from the sun. Despite the challenges, several missions have successfully landed on Venus, sending back valuable data about this enigmatic world. These missions, however, faced a race against time as their instruments succumbed to the intense heat and pressure of the Venusian atmosphere. The images and data they collected painted a picture of a world dominated by volcanoes, lava flows, and vast plains, a testament to the planet's violent geological history. Section 4. A toxic beauty, the Venusian atmosphere. Venus's atmosphere is a fascinating and formidable entity, playing a key role in shaping the planet's extreme environment. Unlike Earth's relatively thin and transparent atmosphere, Venus is enveloped in a dense, thick blanket of gases, primarily carbon dioxide, with clouds of sulfuric acid. This thick atmosphere creates a pressure at the surface 90 times greater than Earth's, equivalent to being 900 meters or 3,000 feet beneath the ocean's surface. The thick carbon dioxide atmosphere acts like a giant blanket, trapping heat from the sun and leading to the runaway greenhouse effect that makes Venus so incredibly hot. The sulfuric acid clouds further contribute to this effect by reflecting sunlight back down to the surface, preventing heat from escaping back into space. This extreme heat has a profound impact on the planet's surface, shaping its geology and influencing its evolution. The Venusian atmosphere is also incredibly dynamic, with winds whipping around the planet at speeds of up to 360 kilometers per hour or 224 miles per hour in the upper cloud layers. These winds are so powerful that they can circle the planet in just 4 Earth days, a phenomenon known as superrotation. The cause of this superrotation is still not fully understood, but it highlights the complex and often unpredictable nature of planetary atmospheres. Despite its hostile environment, the Venusian atmosphere holds clues to the planet's past and may even offer insights into the evolution of Earth's own atmosphere. Scientists believe that Venus may have once had a more Earth-like climate with liquid water on its surface. However, the runaway greenhouse effect transformed the planet into the scorching inferno we see today, a cautionary tale about the delicate balance of planetary atmospheres. Section 5. Planetary Exploration, Unveiling Secrets. Our exploration of Mercury and Venus, though challenging, has provided invaluable insights into the diverse nature of planets within our solar system. Each mission, each image beamed back from these distant worlds adds to our understanding of planetary formation, atmospheric dynamics, and the search for life beyond Earth. The Mariner 10 mission, launched in 1973, was our first glimpse into the hidden world of Mercury. It provided the first close-up images of the planet's cratered surface, revealing a world shaped by impacts and volcanic activity. Subsequent missions like NASA's Messenger spacecraft have further unveiled Mercury's secrets, mapping its surface in unprecedented detail, studying its magnetic field, and providing evidence for water ice hidden in permanently shadowed craters at its poles. Venus, with its thick and toxic atmosphere, has presented unique challenges for exploration. Despite the harsh conditions, several missions have successfully landed on the planet, enduring extreme heat and pressure to send back valuable data. The Soviet Venera missions, for example, provided the first images from the surface of another planet, revealing a desolate but strangely beautiful landscape. More recent missions, like the European Space Agency's Venus Express, have focused on studying the planet's atmosphere, providing insights into its composition, dynamics, and the runaway greenhouse effect. These missions, driven by human curiosity and ingenuity, highlight the power of space exploration to expand our knowledge, challenge our assumptions, and inspire future generations. As we continue to explore our solar system, we unravel the mysteries of our cosmic neighborhood and deepen our appreciation for the wonders of the universe. Our journey has just begun, and countless discoveries await us as we venture further into the cosmos. Section 1. Earth, our pale blue dot. From the inferno of Venus, we journey now to a haven, a beacon of life in the vastness of space, Earth, our home. Seen from afar, Earth is a swirling sphere of blue and white, a delicate oasis in the blackness of space. This pale blue dot, as Carl Sagan famously called it, is the only known world to harbour life, a testament to the unique and precious conditions that make our planet so special. Earth's uniqueness stems from a delicate balance of factors. Our distance from the Sun provides the perfect amount of warmth, not too hot like Venus, nor too cold like Mars. Our atmosphere, a protective layer of gases, shields us from harmful radiation, regulates our climate and allows life to thrive. And of course, the presence of liquid water, the lifeblood of our planet, is essential for all known forms of life. But Earth is more than just a set of favourable conditions. It's a dynamic, ever-changing system, a complex interplay of land, oceans, atmosphere and life itself. The continents drift atop tectonic plates, shaping the landscape and influencing the climate. The oceans, vast and deep, regulate temperature, drive weather patterns and teem with a diversity of life that rivals even the rainforests. And then there's life itself, the most remarkable feature of our planet. From the smallest microorganisms to the largest whales, life on Earth is a testament to the power of evolution, adaptation, and the interconnectedness of all living things. Over billions of years, life has transformed our planet's atmosphere, shaped its geology, and created the conditions that allow us to exist. Section 2, A Symphony of Life, Earth's Biosphere. Imagine a world teeming with life, a tapestry of diverse ecosystems, each home to a unique collection of plants, animals and microorganisms. This is Earth's biosphere, a living, breathing testament to the power of life to thrive in even the most extreme environments. From the lush rainforests to the arid deserts, from the frozen poles to the depths of the oceans, life finds a way. Earth's biosphere is a complex and interconnected web of life. Plants harness energy from the sun through photosynthesis, providing the foundation for food chains that support countless species. Animals, in turn, play vital roles in pollination, seed dispersal and nutrient cycling. Microorganisms, though often unseen, are essential for decomposition, nitrogen fixation and other processes that keep ecosystems functioning. This intricate web of life is a testament to the power of evolution. Over billions of years, life on Earth has diversified and adapted to fill every conceivable niche. From the extremophiles that thrive in boiling hot springs to the deep-sea creatures that navigate the darkness of the abyssal plains, life constantly pushes the boundaries of what's possible. Earth's biosphere is not only a source of wonder, but also a vital component of our planet's life support system. Forests, for example, absorb carbon dioxide from the atmosphere, helping to regulate our climate. Oceans produce much of the oxygen we breathe and play a crucial role in absorbing heat. The biodiversity of our planet provides us with food, medicines, and countless other resources. Section 3. Mars, the red planet, beckons. Leaving the familiar blue and green of Earth, we set course for our next destination, Mars, the red planet. Since ancient times, Mars has captured the human imagination, its reddish hue in the night sky inspiring tales of war, passion, and the possibility of other worlds. Today, Mars beckons us not with legends, but with the tantalizing possibility of becoming a second home for humanity. Mars is a world of stark beauty, a cold, dry desert planet with a thin atmosphere. Its surface, painted rusty red by iron oxide, is a testament to a past when water flowed freely, carving vast canyons and depositing sediments on ancient lake beds. Today, Mars is a frozen desert, but evidence suggests that beneath its surface, liquid water may still exist, perhaps harboring microbial life or offering a resource for future human explorers. Unlike Earth, Mars lacks a global magnetic field to shield it from the sun's harmful radiation. Its thin atmosphere offers little protection from the harsh solar wind, and temperatures can swing wildly, from a relatively balmy 70 degrees Fahrenheit in the summer to a frigid -200 degrees Fahrenheit at the poles. Despite these challenges, Mars holds immense promise. Its day-night cycle is similar to Earth's, and its axis of rotation is tilted at a comparable angle, resulting in seasons like ours, though much longer and more extreme. The presence of water ice at the poles and possibly beneath the surface offers a potential resource for future human missions, and the planet's relatively close proximity to Earth makes it a more accessible destination for exploration than the outer solar system. Section 4. Clues from the past, Martian geology. Imagine yourself as a Martian geologist exploring the red planet's rugged terrain. You'd find a world shaped by both ancient cataclysms and subtle ongoing processes. Towering volcanoes, long dormant, reach towards the thin Martian sky, while vast canyons carved by ancient rivers scar the landscape. Mars's geology tells a tale of two distinct periods. The first, known as the Noachian period, was a time of intense volcanic activity, heavy bombardment from asteroids and comets, and the presence of liquid water on the surface. Evidence suggests that during this early period, Mars may have had a thicker atmosphere, a warmer climate, and even oceans. The second period, the Amazonian, began about 3 billion years ago and continues to this day. During this time, volcanic activity decreased, the atmosphere thinned, and the planet transformed into the cold, dry desert we see today. However, evidence of past water activity is etched into the Martian landscape, from the branching channels of ancient rivers to the layered sediments of dried-up lake beds. Today, Mars is a geologically active world, though much less so than Earth. Marsquakes, while infrequent, still rumble beneath the surface, and evidence suggests that volcanic activity may not be entirely extinct. Landslides, driven by gravity and the changing seasons, reshape the landscape, and the polar ice caps expand and contract, revealing layers of ice and dust that hold clues to Mars's climatic past. Perhaps the most profound question driving our exploration of Mars is whether life ever existed there. Did life, even in its simplest forms, ever find a foothold on this now barren world? The answer, if found, would fundamentally alter our understanding of life in the universe. While no definitive evidence of past or present life on Mars has been found, tantalizing clues keep the search alive. The presence of organic molecules, the building blocks of life, has been detected in Martian soil and rocks. Methane, a gas often associated with biological activity, has been observed in the Martian atmosphere, though its source remains a mystery. The search for Martian life focuses on identifying environments where life could have existed in the past or might still persist today. These include the subsurface, where liquid water may exist, and ancient hydrothermal systems, where heat and chemical energy could have supported microbial life. The search for life on Mars is not just about finding alien microbes. It's about understanding the conditions necessary for life to arise and evolve. By studying Mars, a planet that may have once been more Earth-like, we gain insights into the early history of our solar system and the factors that led to the emergence of life on our own planet. The search for life beyond Earth, whether successful or not, challenges us to expand our definition of life and to contemplate our place in the grand tapestry of the cosmos. As we venture beyond the rocky inner planets and the asteroid belt, we enter a realm of giants where colossal worlds of gas and ice hold sway. Our first encounter is with Jupiter, the largest planet in our solar system, a behemoth that could contain over 1,300 Earths within its vast volume. Imagine a world so massive that its gravity affects the orbits of objects across the solar system, a true king of the planets. Jupiter is a gas giant, composed primarily of hydrogen and helium, the same elements that make up our Sun. However, unlike the Sun, Jupiter lacks the mass to ignite nuclear fusion and become a star. Instead, it remains a planet, albeit a massive one, radiating more heat than it receives from the Sun due to the gravitational pressure deep within its core. From afar, Jupiter's most striking feature is its colourful cloud bands, stripes of swirling gas that encircle the planet at different latitudes. These bands are driven by Jupiter's rapid rotation, which completes a day in just under 10 Earth hours, creating powerful jet streams that whip around the planet at speeds of up to 300 miles per hour. Among these swirling clouds lies Jupiter's most iconic feature, the Great Red Spot, a colossal storm that has been raging for at least 400 years. This anticyclonic storm, larger than Earth itself, is a testament to the turbulent nature of Jupiter's atmosphere. Its swirling red clouds, thought to be colored by organic molecules, have captivated astronomers for centuries. Imagine plunging into Jupiter's atmosphere, a descent into a chaotic and colorful realm unlike anything found on Earth. The pressure would increase dramatically, crushing you with the weight of thousands of Earth's worth of atmosphere above. The temperature would fluctuate wildly, from frigid cold in the upper layers to scorching heat as you descended deeper, approaching the planet's hot, dense core. Jupiter's atmosphere is a complex and dynamic system, with layers of clouds composed of ammonia ice, ammonium hydrosulfide, and water. These clouds create the planet's distinctive banded appearance, with different colors reflecting the varying compositions and altitudes of the cloud layers. The rapid rotation of Jupiter, coupled with its internal heat source, drives powerful jet streams that whip around the planet, creating the swirling cloud patterns we observe. These jet streams can reach speeds of up to 300 miles per hour, generating massive storms and eddies that constantly reshape the Jovian atmosphere. One of the most fascinating aspects of Jupiter's atmosphere is the presence of lightning, which can be thousands of times more powerful than lightning on Earth. These colossal electrical discharges illuminate the Jovian night, offering a glimpse into the turbulent energy within this giant planet's atmosphere. Despite its chaotic nature, Jupiter's atmosphere holds clues to the planet's formation and evolution. By studying its composition, dynamics, and temperature profile, scientists can piece together the history of this gas giant and gain insights into the processes that shaped our solar system. Leaving the swirling clouds of Jupiter behind, we journey outward to encounter Saturn, the sixth planet from the Sun, and arguably the most visually stunning object in our solar system. Imagine a world adorned with a breathtaking system of rings, a celestial ballet of ice and rock that has captivated astronomers for centuries. This is Saturn, the jewel of our solar system. While Jupiter reigns as the largest planet, Saturn holds the title for the most extensive ring system. These rings, composed primarily of ice particles ranging in size from tiny grains to chunks as large as houses, stretch out over 280,000 kilometers or 175,000 miles from the planet, yet are remarkably thin, averaging only about 20 meters or 66 feet thick. The origin of Saturn's rings is still a subject of scientific debate, but the prevailing theory is that they formed from the remnants of a shattered moon or comet that got too close to the planet and was torn apart by its powerful gravity. These fragments, caught in a gravitational tug-of-war, spread out into a thin disk, orbiting Saturn like miniature moons. Saturn's rings are not a single solid structure, but rather a complex system of thousands of individual ringlets, each with its own unique orbit and composition. These ringlets are constantly interacting with each other, influenced by the gravitational pull of Saturn's many moons, creating a dynamic and ever-changing spectacle. Saturn's beauty extends beyond its majestic rings to its diverse and intriguing family of moons. With over 80 confirmed moons, and likely many more awaiting discovery, Saturn's system is a miniature solar system in itself, a celestial ballet of icy worlds, each with its own unique story to tell. Among Saturn's moons, Titan stands out as a true wonder. Larger than the planet Mercury and the only moon in our solar system known to have a dense atmosphere, Titan is a world shrouded in mystery. Its atmosphere, composed primarily of nitrogen with traces of methane, creates a hazy orange glow, obscuring its surface from view. Beneath this hazy veil lies a world surprisingly similar to Earth, albeit a much colder one. Titan's surface is sculpted by rivers, lakes and seas, but instead of water, these bodies of liquid are filled with methane and ethane, hydrocarbons that exist as liquids at Titan's frigid temperatures. Scientists believe that Titan's methane cycle, with methane rain, rivers and seas, may hold clues to the early Earth, before life as we know it emerged. Another intriguing moon, Enceladus, may hold even greater promise for life. This small, icy world, barely wider than the United Kingdom, harbours a hidden ocean of liquid water beneath its icy crust. Geysers erupt from Enceladus's south polar region, spewing plumes of water vapour and organic molecules into space, hinting at a potentially habitable environment beneath the surface. Our understanding of Jupiter and Saturn, these gas giants that dominate the outer solar system, has been revolutionized by robotic explorers sent to unravel their mysteries. These missions, marvels of engineering and human ingenuity, have beamed back stunning images, gathered invaluable data, and reshaped our understanding of these colossal worlds and their intricate systems of rings and moons. The Pioneer and Voyager missions, launched in the 1970s, provided our first close-up glimpses of Jupiter and Saturn, revealing the intricate details of their cloud bands, the dynamics of their atmospheres, and the diversity of their moons. These missions were followed by dedicated orbiters like Galileo at Jupiter and Cassini at Saturn, which spent years studying these gas giants in unprecedented detail. The Galileo mission, for example, dropped a probe into Jupiter's atmosphere, providing the first direct measurements of its composition, temperature and wind speeds. The Cassini mission, orbiting Saturn for over 13 years, revealed the intricate structure of its rings, studied the dynamics of its atmosphere, and even landed a probe on the surface of Titan, providing our first glimpse of this enigmatic moon's alien landscape. More recently, the Juno mission, currently orbiting Jupiter, is focused on studying the planet's magnetic field, its internal structure, and the dynamics of its deep atmosphere. These missions, driven by human curiosity and a thirst for knowledge, continue to expand our understanding of these gas giants, their roles in the formation of our solar system, and the potential for life in their intriguing systems of moons. Our journey through the solar system continues, and as we venture further into the realm of ice giants, prepare to be amazed by the wonders that await us. Our journey through the outer solar system now takes us to a realm of ice and mystery, where giants spin on their sides and frigid temperatures prevail. We arrive at Uranus, the seventh planet from the Sun, a world so tilted that it practically orbits on its side, its poles pointing towards the Sun for decades at a time. Imagine a world where seasons last for decades, where the Sun barely peaks above the horizon for years on end, and where a strange, icy beauty reigns supreme. Uranus, unlike the gas giants Jupiter and Saturn, is classified as an ice giant, a world composed primarily of water, methane and ammonia ices, with a relatively small rocky core. Its pale blue-green hue, a result of methane in its upper atmosphere absorbing red light from the sun, hints at the frigid temperatures that prevail on this distant world. The most peculiar feature of Uranus is its extreme axial tilt, with its axis of rotation tilted at an angle of 98 degrees relative to its orbit. This means that Uranus essentially spins on its side, with its poles pointing almost directly towards the Sun for half of its 84-year orbit. This unusual orientation is thought to be the result of a cataclysmic collision with a large object early in the solar system's history. This extreme tilt has profound implications for Uranus's seasons. For nearly a quarter of its orbit, one pole or the other faces the Sun continuously, while the other half of the planet is shrouded in darkness. This results in seasons of extreme length and contrast, with summers lasting for decades of continuous sunlight, followed by equally long winters of perpetual darkness. Beneath Uranus's serene blue-green exterior lies a world of mystery, its atmosphere and interior holding secrets yet to be fully understood. While Uranus lacks the vibrant cloud bands and raging storms of Jupiter and Saturn, its atmosphere is far from static, exhibiting subtle but intriguing dynamics that continue to puzzle scientists. Uranus's atmosphere is composed primarily of hydrogen and helium, like the gas giants, but it also contains a significant amount of methane, which gives the planet its characteristic blue-green color. Trace amounts of other hydrocarbons, such as ethane and acetylene, have also been detected, suggesting a complex atmospheric chemistry. While Uranus appears relatively bland at visible wavelengths, observations at infrared wavelengths reveal a more dynamic atmosphere. Faint cloud bands, similar to those on Jupiter and Saturn, have been observed, suggesting the presence of atmospheric circulation patterns. Occasional storms, though much smaller and less frequent than those on the gas giants, have also been detected, hinting at the turbulent energy hidden beneath Uranus's calm exterior. The interior of Uranus is equally enigmatic. Scientists believe that beneath its thick atmosphere lies a vast icy mantle composed primarily of water, methane and ammonia ices. This icy mantle is thought to be a supercritical fluid exhibiting properties of both a liquid and a gas under immense pressure and temperatures. Continuing our journey outward, we arrive at Neptune, the eighth and farthest known planet from the Sun. This icy giant, shrouded in a deep blue atmosphere, reigns over the outer reaches of our solar system, a testament to the enduring power of gravity and the surprising diversity of worlds that orbit our Sun. Neptune, like its neighbor Uranus, is classified as an ice giant, its composition and structure similar to its tilted sibling. However, Neptune's atmosphere is a deeper blue, a result of the presence of more methane and potentially other trace gases that absorb red and yellow light from the Sun, leaving behind the predominantly blue hues we observe. Despite its immense distance from the Sun, receiving only a fraction of the sunlight Earth receives, Neptune is a surprisingly dynamic world. Its atmosphere is home to powerful winds, massive storms, and a complex system of cloud bands, suggesting a turbulent and energetic environment driven by internal heat sources. One of the most striking features observed on Neptune is the Great Dark Spot, a colossal storm system similar in size to Earth that was first observed by the Voyager 2 spacecraft in 1989. This storm, characterized by its dark blue color and swirling winds, was a testament to the dynamic nature of Neptune's atmosphere. Imagine experiencing the winds of Neptune, some of the fastest in the solar system, whipping around the planet at speeds exceeding 1,200 miles per hour. These winds, driven by the planet's internal heat and its rapid rotation, create a turbulent and dynamic atmosphere, a stark contrast to the seemingly calm exterior we observe from afar. Neptune's atmosphere, like Uranus's, is composed primarily of hydrogen and helium, with a significant amount of methane giving the planet its characteristic blue color. However, Neptune's atmosphere appears more dynamic and turbulent than Uranus's, with more prominent cloud bands and more frequent storm systems. The exact mechanisms driving Neptune's powerful winds are still not fully understood, but scientists believe that a combination of factors is at play. The planet's internal heat, thought to be generated by the slow gravitational contraction of its core, likely plays a significant role driving convection currents in the atmosphere. Neptune's rapid rotation, with a day lasting only about 16 Earth hours, further contributes to the formation of powerful jet streams that whip around the planet. These powerful winds and the turbulent nature of Neptune's atmosphere create a constantly changing spectacle, with cloud formations appearing, disappearing and evolving over timescales of days or even hours. From bright white methane clouds high in the atmosphere to dark swirling storms deeper down, Neptune's atmosphere is a testament to the dynamic and often unpredictable nature of our cosmic neighborhood. Our journey through the solar system now takes us to the heart of it all, the celestial engine that drives our planetary ballet, the Sun. This giant ball of plasma, a churning inferno of hydrogen and helium, is the source of our light, our warmth, and the very energy that allows life to flourish on Earth. Imagine a celestial furnace, fusing atoms in its core, releasing unimaginable amounts of energy that radiate outward, bathing our solar system in its life-giving glow. The Sun is a star, one of billions in our Milky Way galaxy, but it holds a special significance for us, for it is our star. Its immense gravity holds our solar system together, dictating the orbits of planets, asteroids, and comets alike. Its energy, radiating outward in all directions, provides the light and warmth that make life on Earth possible. At the Sun's core, temperatures reach a staggering 27 million degrees Fahrenheit, or 15 million degrees Celsius, hot enough to sustain nuclear fusion, the process that powers the Sun. Here, hydrogen atoms are fused together under immense pressure, creating helium and releasing enormous amounts of energy in the form of light and heat. This energy then slowly makes its way outward through the Sun's interior, eventually reaching the surface and radiating into space. The Sun's surface, though still incredibly hot at around 10,000 degrees Fahrenheit, or 5,500 degrees Celsius, is a relatively cool region compared to its core. Here we observe a constantly changing tapestry of features, from dark sunspots, cooler regions where the Sun's magnetic field is particularly strong, to bright solar flares, bursts of energy that erupt from the Sun's surface, sending streams of charged particles out into space. Leaving the Sun's fiery embrace, we venture back out into the colder reaches of our solar system, but our journey is far from over. Between the orbits of Mars and Jupiter lies a vast and ancient region, a celestial shooting gallery where remnants of the early solar system still dance around the Sun. The asteroid belt. Imagine a region of space littered with rocky debris remnants of a planet that never formed, or perhaps the shattered fragments of a world torn apart by Jupiter's immense gravity. The asteroid belt is home to millions of asteroids ranging in size from tiny pebbles to dwarf planets hundreds of kilometers across. These rocky remnants are not evenly distributed, but rather clumped together in groups and families, their orbits influenced by the gravitational pull of Jupiter and other planets in the solar system. Despite the vast number of asteroids in the belt, the region is surprisingly sparse. Spacecraft traveling through the asteroid belt have a very low probability of colliding with an asteroid, as the distances between these objects are vast, often millions of kilometers apart. The asteroids themselves are a diverse bunch, their compositions reflecting the different conditions that existed in the early solar system. Some asteroids are rich in carbon, while others are metallic, suggesting they formed in different regions of the protoplanetary disk, the swirling cloud of gas and dust that gave rise to our solar system. Venturing beyond the asteroid belt, we journey into the realm of ice and darkness, where the Sun's light and warmth are but faint whispers. Here, beyond the orbit of Neptune, lies a vast and mysterious region known as the Kuiper Belt, a frigid realm where icy remnants of the early solar system circle the Sun in a slow and stately dance. Imagine a region of space so distant and cold that even the Sun's warmth is barely perceptible, a realm of icy wanderers, frozen in time since the formation of our solar system. The Kuiper Belt is home to trillions of icy objects, remnants of the early solar system that never coalesced into planets. These objects, composed primarily of frozen water, methane and ammonia, are the building blocks of comets, icy wanderers that occasionally venture into the inner solar system, their tails blazing across the sky as they are heated by the Sun. The most famous resident of the Kuiper Belt is Pluto, once considered our 9th planet, but now classified as a dwarf planet. Pluto, along with its largest moon, Charon, and several smaller moons, is a fascinating world in its own right, its surface sculpted by icy volcanoes, nitrogen glaciers, and impact craters. The Kuiper Belt is a region of immense scientific interest, as it holds clues to the formation and evolution of our solar system. By studying the composition, orbits and dynamics of Kuiper Belt objects, scientists can piece together the history of our cosmic neighborhood and gain insights into the processes that led to the formation of the planets and other celestial bodies we observe today. Our journey through the solar system concludes in the outermost reaches, a realm of icy wanderers and faint whispers of sunlight. Here, in the vast expanse beyond the Kuiper Belt, lies the Oort cloud, a hypothetical sphere of icy objects thought to extend trillions of kilometers from the Sun, a cosmic repository of remnants from the earliest days of our solar system. Imagine a region of space so vast and sparsely populated that it's often described as a cosmic vacuum cleaner, its gravitational influence gently nudging icy objects inward, sending them on long, looping journeys around the Sun. Comets, those icy wanderers that occasionally grace our skies with their brilliant tails, originate from these distant realms, their orbits perturbed by the gravitational pull of passing stars or giant molecular clouds, sending them on long, elliptical journeys that can take thousands or even millions of years to complete. As comets approach the Sun, their icy surfaces begin to vaporize, creating a glowing coma or head, and often two distinct tails, a dust tail, composed of particles left behind by the vaporizing ice, and an ion tail, created by the interaction of the comet's gas with the solar wind. The study of comets provides a unique window into the early solar system, as their icy compositions are thought to preserve the primordial materials from which our solar system formed. By analyzing the light reflected from comets, scientists can identify the molecules and compounds present in these icy wanderers, providing clues to the conditions that existed billions of years ago. Our journey through the solar system has taken us from the scorching heart of the Sun to the frigid outskirts beyond Neptune, from the rocky planets of the inner solar system to the gas giants and icy worlds of the outer solar system. We've encountered worlds of unimaginable beauty and diversity, each with its own unique story to tell, its own secrets waiting to be unlocked. But our exploration of the cosmos is far from over. The solar system is but a tiny speck in the vastness of the universe, and countless wonders await us as we venture further out into the great unknown. As our journey through the solar system comes to an end, we find ourselves back on Earth, our pale blue dot, a haven of life in the vastness of space. We've travelled from the scorching surface of Mercury, where the Sun dominates the sky, to the icy realms of Neptune, where sunlight is but a faint whisper. We've explored gas giants with swirling storms larger than our entire planet, and marvelled at the intricate dance of rings and moons around Saturn. Along the way, we've encountered worlds both familiar and strange, each with its own unique story to tell. We've learned about the power of gravity, the delicate balance of planetary atmospheres, and the incredible diversity of worlds that can exist around a single star. We've glimpsed the raw beauty of the cosmos, from the fiery heart of the Sun to the icy depths of the Kuiper Belt. But most importantly, perhaps, we've gained a deeper appreciation for our own planet, our cosmic oasis. Earth, with its life-sustaining atmosphere, its vast oceans and its teeming biosphere, is a precious and fragile world, a reminder that we are part of something much larger than ourselves. As we look up at the night sky, we are reminded that our journey of exploration is far from over. The solar system, for all its wonders, is but a tiny corner of the universe, a single star system among billions in our galaxy and countless galaxies beyond. The universe is vast, ancient, and full of mysteries yet to be unraveled. The human spirit of exploration, however, knows no bounds. Driven by curiosity, a thirst for knowledge, and a desire to understand our place in the cosmos, we continue to reach for the stars, pushing the boundaries of technology and human ingenuity to explore the universe around us. We send robotic explorers to distant planets, their cameras acting as our eyes, their instruments as our senses, beaming back data that expands our understanding of the cosmos. We build telescopes of unimaginable power, capable of peering into the farthest reaches of space and time, revealing the secrets of distant galaxies and the echoes of the Big Bang. And one day, perhaps soon, we will venture beyond our own solar system, carrying with us the dreams and aspirations of humanity to explore new worlds, to seek out other life forms, and to unravel the mysteries of the universe. The quest for knowledge, for understanding, is a never-ending journey. And each new discovery, each step forward, brings us closer to unlocking the secrets of the cosmos. The exploration of space is not merely an academic pursuit, it's a testament to the human spirit, a reflection of our innate desire to explore, to discover, and to push the boundaries of what's possible. It's a journey that challenges us to think differently, to imagine the impossible, and to dream of a future where humanity becomes a truly spacefaring civilization. And as we continue this journey of exploration, we carry with us the knowledge that we are part of something much larger than ourselves. A cosmic tapestry, woven together by the laws of physics, the evolution of stars, and the endless dance of matter and energy. Our exploration of the solar system has not only expanded our knowledge of the universe, but has also profoundly changed our perspective on our place within it. We are no longer the center of the universe, as once believed, but rather inhabitants of a small, rocky planet orbiting an average star in a galaxy teeming with billions of other stars, each potentially harboring its own system of planets. This realization, far from diminishing our significance, actually elevates it. We are the universe becoming conscious of itself, as Carl Sagan once said, capable of comprehending the vastness of the cosmos and our place within it. We are the product of billions of years of cosmic evolution, the descendants of stars that lived and died, their ashes scattering across space, eventually coalescing into the very atoms that make up our bodies. We are stardust, as Joni Mitchell so eloquently put it, and in our exploration of the universe, we are essentially coming to understand ourselves, our origins, and our place in the grand scheme of things. The universe is a vast and mysterious place full of wonders yet to be discovered, but it is also our home, the only home we know. As we continue to explore its depths, we do so with a sense of awe, wonder, and a profound responsibility to protect and preserve this precious pale blue dot we call Earth. For it is here, in this cosmic oasis, that our journey began, and it is here that the future of humanity unfolds. Thank you for watching. Don't forget to like and subscribe for more cosmic exploration.